Hello. This is the last video of this chapter. This chapter was chapter 7 about multiple regression, linear regression with multiple regressors, and so we are going to discuss briefly the control variables and then I will show you how to work on homework 3. And then, if time permits, we are going to start the next chapter, chapter 7, about inference, hypothesis test, and confidence interval with multiple regressors. So, okay, let's start. What are control variables? It's simple. So we are including multiple regressors in one regression model. And I explained the main motivation to include multiple variables is to remove or mitigate the omitted variable bias. So when you omit an important variable, then that omission causes some bias in your estimators. So that can mislead your estimation. For example, like the true parameter is positive, but your estimator may be negative because of the bias. Then so if you think about, like, say you are the president, you'd like to increase the minimum wage, then estimating its effect is really important. It can change the whole economy, and then removing those kind of bias is super important. So related to that point, I would like to distinguish the multiple regressors into two types. This is important. This distinction is important to make the correct interpretation of the estimators and to think about what you can say and what you cannot, or why still you need to include those variables. So simply speaking, in a regression with multiple regressors, still there is usually one variable of interest. So you are interested in usually one of them. Like in our example, we are interested in the effect of class size on the student-to-teacher ratio on the test scores. So we would like to estimate this causal effect, but still we consider multiple regressors because we need them, and we learned why we need to include the percentage of English learners. So when you include only one variable, the student-to-teacher ratio, there are still some missing information about the school districts and other factors that determine the test scores. So those missing information, missing variables, omitted variables can cause bias. So to minimize this bias, you have to include more variables. We call those variables as the control variables because we are including them just to control for the unobserved missing information. So like in this case, percentage of English learners captures the potential unobserved, like a living environment or their family environment, like associated with being a non-native English speaker, for example. So it is important to understand what you are interested in and what you have to include to make the estimator of your interest correct. So the control variables are just serving as a sidekick. It's not a main variable, but still they are very important. And so simply speaking, even if you are not interested, I'm not interested in the percentage of English learners. It may be important factor in test scores, but I cannot change the percentage of English learners. It is not my choice, or you cannot force, or you cannot you cannot bring more learners or move away the learners at all, still not we are including those variables, because if not, you are in trouble. So to avoid those problems, we have to include them. So think about the case. Like as I said, when you estimate the effect of class size on test scores, in principle, you want to hold all the other factors constant. Like all the other factors that have impact on the test scores must be fixed constant, ideally, if possible. So those factors may include outside learning opportunities, or like parental involvement, or your family income, or parental like say education, or like all these things like economic situations, blah blah blah. So this is purely just a hypothetical setup, and if we could run a perfect experiment, then we are going to randomly assign students to different class sizes without looking at their other factors. Like so when you randomize, you should not use other informations like family income, parents' education, where they live, or so those should not be considered in those random assignment. Then you are going to get the ideal data to estimate the causal effect of class size on test scores. But of course, it is not possible. Experiment is not possible. So we would like to mimic this. By the way, if this experiment was possible, if you have data generated from this perfect experiment, then you don't need control. Because by perfect randomization, you are already controlling for all the other factors by not considering them. Randomization without considering other factors already makes all the other factors constant. However, this kind of experiment, so in that case, you don't need multiple regressors. You can simply regress test scores on experiment. That's it. So if you had perfect experiment, of course you don't have that. So we need to think about the additional problems. So we call usually the data we observe is observational data. We do not randomize. We do not do any experiment. We are just observe how school districts do and what's their test scores. So it is purely observational. And then because we could not randomize, and in this data, the choice of schools, like class size, the choice of school must be dependent on other factors, like say family income. So if you are from a rich family, then you are going to find a better school district where the school sizes are small. So it is not random. So the choice is not random anymore. Then from this point, the other factors is not held constant. The other factors are not held constant in assignment of the class size. So you have to worry about the omitted variable bias or the conditional mean independence. There must be some systematic relationship between class size and, say, family income. If you do not observe family income, then it causes problems. So in this case, because it is not perfectly random and other factors are not held constant in the assignment, we have to include control variables, which ideally, if you could observe family income directly, including that variable into the regression would be better. But suppose that and like family income is not available in many cases, then instead of the omitted variable itself, you may alternatively include percentage of English learners. So if the percentage of English learners is another proxy variable, it's another kind of, if it is related to the omitted variable family income, then including the percentage of English learners still helps. So, but it is not, you cannot interpret this variable as a cause and effect variable. So it is just it is just trying to fix all the other unobserved variables constant and try to help recover the omitted variable as much as possible based on your data. So you cannot say much about this guy in our setup. And let's think about even more expanded regression model. Test score, as usual, test score is regressed on intercept and student to teacher ratio and percentage of English learners, and we additionally include lunch program percentage. So this is the percentage of students who receive free or subsidized lunch. Usually, as you can see, low income students get a free lunch or subsidized lunch. So this percentage captures the percentage of students from poor families. So this may be a better variable to control for the family income. So if you agree that the family income is an important variable, then if the family income is not available, then you need to think about this variable as an alternative to minimize the effect of unobserved family income. So then in this regression, it is clear that we would like to find causal relationship between test score and student to teacher ratio. The other guys are not our variables of interest. So we are not interested in their effects on test scores, even though we need them. So we need them to help this estimate correct. For this estimate to be correct, we need to include these variables, control variables. As I said, they are controlling for family income, not themselves. And then, but you may think that if you are interested in this or this, that is possible, but you need a totally different story. So you need to set up a different story, like what if the percentage of English learners increases, then what would be the increase or decrease in the test score? And then why do you need it? What is the experiment behind it? You may think about those cases, those arguments, but that's not our focus, and you have to think what is the experiment you would like to have. For example, a big problem here is for example, so suppose that you are interested in the percentage of free lunch. Free lunch percentage has a huge impact on test score. So compare like these two. So 1% increase in free lunch percentage affects minus 0.5, has a nearly half of the student to teacher ratio. So for example, instead of reducing student to teacher ratio by 1, you may reduce lunch percentage by 2% point. They are nearly equivalent, or this is bigger. 2% point change in lunch percentage has a bigger effect than 1 unit change in student to teacher ratio. So -1 and -0.5 something. But that interpretation is wrong because it does not say that. So if higher lunch percentage decreases the test score, then consider, does that mean if you abolish free lunch program at all? So suppose that now from tomorrow we are not going to give out any free lunch to any student, no matter what your family income is. Then would the test score increase? No, never. So free lunch itself is not does not have causal effect on test scores. So for example, usually when you use this as a variable of interest, you want to say that what happens if you expand the eligibility of free lunch, then by 10% point of students, then what would be the effect on the test scores? However, then if you want to estimate that, then the other things may not be good, and the variation in the lunch percentage does not show the variation in eligibility. So including this variable is needed, but that does not imply this coefficient has a nice interpretation. So then what is -0.547? It's not easy to interpret. There is no direct interpretation of this guy. But because of this guy, we can interpret student to teacher ratio better. -1.0 must be more correct than before. Previously, the estimate was, let me show you, where was it? Previously, it was -1.1 without free lunch. So at this point, we only considered student to teacher ratio and percentage of English learners. And by including one variable, percentage of English learner, the coefficient changed from -2.2 to -1.1. And so I explained this difference as the omitted variable bias. But as you just saw, if you include additional variable here, then -1.1 changes to -1. So 0.1, the difference 0.1 is another omitted variable bias caused by missing the free lunch, missing the unobserved factors that is related to free lunch. So including more control variables will fix the omitted variable bias better. So that is an important conclusion of this chapter. And at the same time, interpretation of these control variables is not easy, and you should be careful in interpreting them. So that's the end of this chapter. I'm not going to go over all the remaining slides. So they are like mathematics, and basically I gave you all the ideas. So I want you to just have the intuition. That should be enough. Okay, I will come back with homework 3. See you later.